We're going to begin to learn about two very special classes of functions that are very different from everything we've learned about so far, because the things we've been learning about so far were either polynomials or rational functions, which are based on polynomials. So the first one we're going to look at is called the exponential function with base a, and it's a to the x. Now we have to put a couple restrictions. We only want a to be positive, otherwise things get really confusing with the graph. And we don't want a to be 1, because 1 to any power is just 1, it's just boring. Okay. Now the second class of functions, the logarithmic function with base a, is written log base a of x, and it has the same two restrictions on a. Now, you may be confused because this one makes sense. Okay, so if a is 2 to the x, whatever x I can plug in, I know what 2 to that power is, or at least my calculator does. Okay, this one, well, what in the world is a logarithm? Now, the way we define logarithms is a little bit backwards. Okay, I have a friend that I know that I could not pronounce her first name for about the first 5 months I knew her. She's from Laotian. It was really complicated for me to learn, even though she tried really hard. So, for a very long time, when I first knew her, if I were speaking about her to anyone else that we both knew, I wouldn't say her first name, because I couldn't pronounce it. I would refer to her by her daughter's name and say this, for clarity, we'll say, she's Jill's mom. Okay? Now, everyone knew who I was talking about. They knew Jill, they knew Jill's mom. But that wasn't really her name, it was just a roundabout way of referring to her. The same thing happens with logarithms. We're not actually going to define a logarithm on its own. The definition of the logarithm is that it is the inverse of the exponential. Meaning, if y equals log base a of x, this only happens if, when we switch x and y and put an exponential, it turns into x equals a to the y. Okay? Now, this comes with warning number 18. Because these two are completely tied together, if we look at this one, we notice that a to the y, that's always a positive number, which means that x here must always be a positive number. So the domain of a logarithm, or the only thing you're allowed to plug into a logarithm, is a positive number. Okay? Now, because they are inverses of each other, they must satisfy the definition of inverse functions, meaning if I compose them in either order, I just get x. So this means that if I take a logarithm base a and plug an exponential base a inside it, I must just get x. And if I take an exponential base a and plug a logarithm inside it, I must just get x, because they are defined to be inverses of each other. Now, I want to look at the graphs. Okay, this is the graph of y equals a to the x. Okay, now this is actually assuming that a is bigger than 1. Okay, if a is less than 1, say suppose a is 1/2. Well, if we were trying to graph 1/2 to the x, this is the same as 2 to the negative 1 to the x, or 2 to the minus x, which means we never have to deal with smaller a because we can just use a graph transformation, in this case a reflection, with bigger a. Now, exponentials will always have this nice swoopy curve. They have an asymptote on one side and they shoot up on the other. In fact, it's an interesting feature of asymptotes, or of exponential functions, that this side here grows faster than any polynomial function you can think of. Okay? Now, there are two special points that every exponential function has. If you plug in x equals 0 to an exponential function, I get a to the 0, and anything to the 0 is 1. So every exponential will go through the point 0, 1. And if you plug in x equals 1, you get a to the 1, which is just a. So every exponential will go through those 2 points. Now we know how to find the inverse graph of any graph. We take it and we flip it about the line y equals x. That must mean that this is the graph of a logarithm. Again, we're assuming a is greater than 1, because if it's not, we can use the same kind of trick and do it as a reflection. Okay. Now, we notice that this time the asymptote is a vertical asymptote, and it grows over to the right. logarithms grow slower than any polynomial function there is. And they also have two very special points, okay? And they're found by turning these ones on their head, meaning switching x and y. So because every exponential goes to the point 0, 1, every logarithm goes to the point 1, 0. Meaning log base a, no matter what the a is, of 1 is always 0. And because every exponential goes to the point 1a, every logarithm goes to the point a1. Meaning that log base a of a is always 1, no matter what a is. Now from these two basic graphs, you can do any kind of regular old graph transformation that we previously learned, and you'll get a graph of a different exponential or logarithm.